Welcome, everyone. A very warm welcome from a freezing cold and wintry Washington, D.C. I would like to welcome you to this first in the knowledge series on pumped storage hydro. Thank you for joining us for the webinar entitled Pumped Storage Hydropower from Design to Performance, which we are jointly hosting with the International Hydropower Association. My name is Fanny Misvedringius, and I'm one of two managers of the Energy Sector Management Assistance Program, which is a partnership between the World Bank Group and over 20 donors to help our partner countries reduce poverty and boost growth through sustainable energy solutions. Power systems around the world are changing fast. Countries are bringing on more solar and wind, expanding electricity access, and meeting rising demand all at once. That combination is putting real pressure on power system reliability and flexibility. In that context, hydropower continues to play a central role. It delivers renewable energy at scale, and just as importantly, it provides the flexibility and reliability that modern power systems need. That is what allows countries to deliver more electricity to more people without increasing emissions. Through ESMAP, as well as its investments, the World Bank Group supports hydropower development in our partner countries. ESMAP specifically helps governments develop hydropower and pumped storage hydropower projects from early identification to bankable investments. That includes system planning, project preparation, policy design, and investment mobilization across the project life cycle. But pumped storage hydropower is not one single solution. Pumped storage hydropower projects differ widely. Cost, performance, environmental and social impact, and energy services all depend on site conditions, system needs, and design choices. For governments and system planners, that creates a complex set of decisions. Choosing the right configuration means balancing flexibility needs, environmental and social considerations, development timelines, and cost, often under uncertainty. That's exactly what today's session is about. We are pleased to be joined by power sector practitioners and colleagues from the International Hydropower Association. We will begin with a perspective from Morocco on the Ifasa pumped hydropower project, a pioneering project for the region that demonstrates the value of pumped storage for power system planning as national energy systems evolve. We will then move to a technical discussion on pumped storage design and performance anchored in experience from the Nord-de-Drance project in Switzerland, one of the largest and most advanced pumped storage hydropower facilities in Europe. Together, these examples will show how pumped storage can support stable, resilient power systems as countries bolster energy security and expand electricity access. And we're looking forward at the end to your questions and answers, to your questions and answers session. Thank you. And with that, let me hand it over to my colleague, Bente Brunes. Bente Brunes is our hydropower lead at ESMAP, and she'll be the moderator for today and begin the session. Over to you, Bente.
Many thanks, Fanny, and many thanks for your very good welcome remarks. I would also like to introduce the agenda briefly for today's webinar. So, following a bit of housekeeping, we will continue on to the introduction of the pumped storage hydropower project in Morocco. And then we will have a more of a deep dive into the design, performance, the system value of pumped storage hydropower, along with the presentations of different solutions. After these presentations, we will have a Q&A round, and we really encourage all of our participants to start typing their questions as we go. You also have the opportunity to upvote these questions as we move forward. But let me begin with the housekeeping. This webinar is being recorded and it will also be made available on our ESMAP website after this. Please post your questions in the Q&A box below. We do have a live interpretation available for this webinar for French and English. If you find the globe icon at the bottom of the screen and then select the language you would like to listen in, you will also hear our interpreters. Publications and useful links will be posted in the chat. So let me then introduce the first speaker today. Nureddin Citroen is a senior energy specialist at the World Bank's Rabat office. He leads the institution's energy projects and initiatives in Morocco, and Nureddin brings extensive experience from the energy consultancy sector, having contributed to the design and follow-up. At the World Bank, he focused on delivering impactful, scalable solutions that strengthen the energy sector's resilience, sustainability, and affordability. So please, over to you, Nureddin, and please share your presentation.
Thank you, Binti. Thank you, Fanny, for the nice introduction. Let me first share my presentation. Okay, do you see my presentation now?
Yes, we can see your presentation. So if you can just change to presenter mode. Thank you.
Is it okay now? Can I start?
Yes, please start.
Yes. Let me now switch to French since my presentation is in French, but I would be very happy to take your questions both in English and in French. Donc, je m'appelle Nureddin Citroen, je suis spécialiste principal en énergie à la Banque mondiale et je suis basé au bureau de Rabat au Maroc. C'est un plaisir pour moi d'être avec vous aujourd'hui pour vous présenter un projet très important dans notre portefeuille. C'est un projet de station de transfert d'énergie par pompage qui s'appelle STEP IFHSA. On l'appelle IFHSA relativement à la région dans laquelle le projet sera implanté et qui se trouve au nord du Maroc. Donc, avant d'entrer dans les détails, j'aimerais plus ou moins faire un état des lieux d'un point de vue contexte stratégique du projet, pour rappeler que le Maroc est un pays qui est pauvre en énergie. Hein. Donc, on a un taux d'indépendance énergétique qui ne dépasse pas 14%. Soi-disant, 87% des besoins énergétiques du Maroc sont importés. Et même en parlant du secteur de l'électricité, qui est aussi une partie importante dans ce mix énergétique, 60% de la production électrique provient du charbon. Et donc, voyez l'importance aussi bien sur le plan climatique que sur le plan aussi financier pour le pays, pour vraiment aller dans une transition énergétique, ce que le Maroc a fait à partir de 2009. Donc, elle s'est inscrite dans une démarche, dans une transition énergétique très importante avec des ambitions qui vont jusqu'à 52% de renouvelables dans le mix énergétique à partir de l'année 2030. Mais force est de constater que l'évolution vers cet objectif ambitieux a toujours été entravée par plusieurs problèmes d'ordre réglementaire, mais surtout même d'ordre réglementaire, il y a l'aspect technique derrière, à savoir que le mix marocain est basé sur des technologies qui sont moins flexibles et donc le développement massif de renouvelables risque de compromettre l'intégrité et la stabilité du réseau électrique national. Et donc, le Maroc s'est inscrit dans cette approche de développer la flexibilité de réseau, notamment à travers le développement de projets de stations de transfert d'énergie par pompage. Pourquoi? Parce que les énergies solaires, comme vous le savez, éoliennes, présentent des pointes de production qui ne correspondent pas à la demande de pointe. Et là, je tiens à rappeler que le Maroc euh, a une courbe de charge qui présente deux pointes, une pointe vers midi, une pointe vers le soir, et bien entendu qui nécessite une certaine flexibilité dans la gestion de la production. Donc, la gestion d'intermittence reste centrale et donc c'est pourquoi donc le Maroc a lancé un programme de 1000 mégawatts de hydropower storage plants qui consiste en une centrale déjà livrée en 2024, à savoir Abdelmoumen, qui présente une puissance de 350 mégawatts et deux projets en parallèle qui sont le projet de Step El Menzel de 362 mégawatts et notre projet IFSA de 300 mégawatts. Sachant que le Maroc n'est pas nouveau dans le développement des steps. Le Maroc a déjà développé sa première step en 2004 d'une puissance de 464, mais c'était pas avec la nouvelle technologie de variation de vitesse qui permet de mieux gérer l'intermittence. Donc, la perspective était plus vers un arbitrage énergétique que l'intégration du renouvelable. Je me permets de vous rappeler un petit peu le principe. Donc, nous avons un bassin supérieur, un bassin inférieur, et nous avons une conduite hydraulique qui lie les deux. Et entre les deux, il y a donc les machines, les turbines, qui peuvent fonctionner aussi bien en mode pompage qu'en mode turbinage. Et bien entendu, pour évacuer ou absorber l'énergie du réseau, nous avons une liaison électrique qui consiste en des transformateurs et un poste de transformation qui relie au réseau national. La zone du projet, le projet se trouve au nord du Maroc, donc plus précisément à 14 km à l'est de la route reliant Chefchaouen à Tétouan. Et donc, il se trouve aussi à la confluence entre deux rivières, à savoir Oued Laou et Oued Saram, à 3 km d'une centrale classique existante qui date des années 40. Donc là, à droite, vous allez voir un peu l'image Google de la position géographique du projet. Bien entendu, vous allez aussi en bas voir les deux réservoirs supérieurs et inférieurs. Justement, en parlant des deux réservoirs, voilà un petit peu l'étendue de comment ils vont être disposés. Donc, nous avons un bassin supérieur et un bassin inférieur qui présentent un petit peu la même donc emprise en termes de surface. Donc, on parle de 6 hectares, une capacité de 800 000 mètres cubes d'eau qui va être donc turbinée et pompée dans un circuit qui est fermé. Et les deux réservoirs vont utiliser la technologie digue en rochement, ou ce qu'on appelle en anglais rockfill. L'usine sera souterraine. Elle présentera deux groupes turbines pompage. Pourquoi? Parce qu'on veut une certaine modularité, étant donné que le Maroc présente une réserve de gestion de la flexibilité de 300 MW. Donc, c'est 2 fois 150 qui permettra un petit peu de moduler l'utilisation de la centrale. Entre les deux bassins, donc on a donc une liaison hydraulique qui avoisine les 2 km, plus précisément 1,7 km, bien entendu avec une galerie inférieure de 162 mètres. Un peu plus en détail, donc on n'a pas nécessairement 800 000 mètres cubes, mais ça va être quelque chose comme 793 000 mètres cubes avec une altitude de 934. Le circuit hydraulique pour le projet donc, est constitué d'une conduite forcée enterrée dans une tranchée, donc pas nécessairement souterraine, avec un diamètre de 3 mètres et un débit un débit de turbinage de 44 mètres par seconde, mètres cubes par seconde, avec un puits vertical revêtu en béton de 205 mètres et 3 mètres de diamètre et une galerie horizontale de 33 mètres avec 3 mètres de diamètre. L'usine souterraine sera composée de deux cavernes. Une caverne qui va abriter les équipements électriques, notamment les transformateurs, et une caverne qui va abriter les deux turbines, turbinage, donc réversible, turbine pompage. Nous aurons aussi un cheminée d'équilibre, une galerie inférieure, un bassin supérieur qui présente un peu la même chose que la même capacité que le bassin inférieur, supérieur, et puis la station de pompage qui permet de faire l'appoint d'eau parce que à un certain moment il y aura de l'évaporation, donc il va falloir faire l'appoint en eau. Ça, c'est le profil, le vue en profil de la centrale. Donc, donc la dénivelée entre le réservoir supérieur et inférieur avoisine les 750 mètres, 753 mètres. Donc, il est très important aussi de signaler la différence entre le débit de turbinage et le débit de pompage. Donc, généralement, on turbine avec un débit plus important que le débit de turbinage. Donc, 2 fois 22, ça fait 44 mètres par seconde versus donc 37 mètres par seconde, mètres cubes par seconde. Le nombre de turbines, c'est 2. La puissance en turbinage et en pompage, c'est 300 mégawatts. Mais à noter aussi la différence en termes de production pour dire que la centrale présente à peu près 80% en termes de rendement, ce qui veut dire qu'on pompe une quantité d'énergie sous forme d'énergie potentielle, mais en production, on produit un peu moins. Donc, ma dernière slide, c'est lié à la connexion de la centrale, de la STEP avec le réseau national. Ça va se faire à travers une liaison 400 kV sur deux postes, le poste Beni Hassan et le poste Walili, avec une liaison de double terme. Donc, en termes de budget, donc on avoisine les 3 à 4 milliards de dirhams. Bien entendu, les études détaillées sont en cours pour vraiment affiner ces valeurs. Et en termes de planning prévisionnel, les études détaillées viennent de commencer. En principe, les appels d'offres vont commencer vers le Q3 2027 pour un début du travaux 2027 et la centrale est prévue d'être mise en service à partir de début 2031. Donc voilà, j'espère ne pas avoir tardé dans la présentation des détails, mais je reste bien entendu à votre disposition si vous avez des questions au sujet de notre projet. Merci.
Thank you so much, Nuruddin, and thank you for a very insightful presentation to the IFASA project. Now I would like to welcome Dr. Selim Saya. He's an expert as hydraulic engineer with over 26 years of experience in hydropower and pump storage hydropower projects worldwide. He holds a PhD from EPFL in Switzerland, and he is hydropower business lead at Lombardi Group. Dr. Saya has led and reviewed several projects across Europe, Africa, Australia, the Americas, Asia, and Middle East. These reviews cover all phases from feasibility projects to construction and rehabilitation. So today we will learn more on pump storage hydropower from him and then also have more insights into his expertise, which includes hydraulic structures, pump storage, and so on. So over to you, Selim.
Thank you, Bente. So today I will have a small talk about the basics of pump storage with relation to the design and the performance. All the examples are practically based on our past experience and sometimes some research. So the outline of the presentation, we will start with a general overview on the pump storage. I will explain a bit the difference between closed loop and open loop as a return to the basic principle, give you a couple of examples around the world for some specific pump storage schemes that being designed and have some specific features. We'll speak a bit about the global presence in pump storage, the head vs length, and the power vs energy. Then we selected a couple of examples related to the design choices, where a designer need to decide on some general principle before starting the design activities. I will talk also about the energy transition and the role of PSP in such transition. We will talk also about ancillaries and some design challenges. The picture that you can see here on the slide is not a castle. It's one of the oldest pump storage scheme in the northern part of Switzerland, near the Schaffhausen Cascades. It was commissioned in 1907. It is 5 megawatt of capacity. This capacity you might think it's a small one, but at that time when we were using horses to transport, building a pump storage scheme was really a great achievement. So a difference between closed loop and open loop. So let us start with the most common that we see it often where we have big lakes, the open loop. So practically open loop is hydraulically connecting two existing water bodies. At least one of the reservoir should be a part of a natural water system, means we have a river flow. It has lots of positive key characteristics. It doesn't require to build two reservoirs, so lower capital cost. It can use existing dams as the upper reservoir, and sometimes it's associated with longer duration storage. Some also feature of the open loop, it has less water head variation, which allow a better flexibility for the pump storage scheme. The cons of such open loop concept is it might have some environmental permitting challenges because it will be using existing lakes or existing reservoir. Closed loop are commonly started to be designed maybe the past 10 years, I would say. We are not seeing lots of closed loops specifically when we have to build two new reservoir from scratch. So those are definitely capex consumption. We have to be sure that they have enough energy duration, because while building two reservoirs, you need big volumes to generate a longer duration. The good thing in closed loop is practically you can build it wherever you want when you have where you have the good topography. A couple of examples of pump storage schemes that are neither very typical. This one comes from Austria, Molen pump storage scheme, capacity of 300 megawatt. It's under design. So they opted to build a powerhouse close to a new reservoir to be built downstream. And the powerhouse, as you can see here, is in a shaft. This kind of configuration allows really to reduce the capex instead of building powerhouses below ground or in big cavern. It has a very short waterway system, and the particularities is that they provided an underground upper reservoir built entirely in cavern in the Australian Alps. Another pump storage that we've been working on comes from the experience in Ontario. This is a very particular one because it corresponds to a very big upper reservoir of around 30 million cubic meter of water. And it's using somehow, let us say, special intakes below the lake just to avoid disturbing the environment, building intakes directly at the river shore. They inspire such intake from nuclear intake technology, where practically you build series of small intakes at the bottom of the lakes. Other impressive pump storage scheme recently commissioned in Switzerland is Nord-de-Drance. Nord-de-Drance started the design activity in 2006 almost, and it was commissioned a couple of years ago. This is very particular project because it became kind of benchmark for recent state-of-the-art pump storage scheme around the world. I see lots of also clients from Australia building Snowy visited this project to get some ideas about how it was developed. It has a very nice configuration. They are using two existing artificial reservoir in the Swiss Alps, and they had increased heightened the upper reservoir dam just to have enough capacity. As you can see on this slide, it's really complex underground works with big cavern, long tunnels, access tunnels. The particularities is that it has a very nice flexibility feature. They opted, Alpiq, the owner, to have two different waterway system, each one feeding 3 turbines. As you can see here, you have 2 pressure shaft and 2 tail race tunnel. This configuration, if we are able to adopt it, it gives some flexibility, especially during maintenance. Another impressive under construction project is Snowy 2.0 in Australia. So this project is actually under construction. Hopefully it will be commissioned this decade. The design started in 2015, I would say. And there is some particular feature of this project. Definitely it has very long tunnels. But one of the main feature is what we call a load index. And this load index is practically the static pressure multiplied by the tunnel diameters. In the present case, as you can see on the upper left graphics, the red histogram of Snowy shows that the load index is one or the highest in the world, practically higher than one of the biggest one recently commissioned in the kind of 20 years ago, Grand Dixence. So this load index defined practically the complexity of designing and building the waterway system. And it's a nice practically factor to understand how much the designer and the owner might suffer while designing and building such major schemes. This is a global picture of where pump storage are being, let us say, built or they exist. So this is a nice picture inspired from the U.S. Department of Energy. I would say we are a bit more than 160 gigawatt of capacity around the world. Definitely, we are seeing a strong push to build more pump storage scheme. Us as designers, we all know that practically now pump generation scheme is maybe slightly less than the request of designing pump storage scheme, and there is a clear trend of the market regarding this technology. I would like also here to introduce a layout feature, which is kind of rule of thumbs. It is what we call the head vs the length of the waterway. So practically, when you want to start from scratch designing a pump storage scheme, you divide the length of the horizontal waterways with the head, static head of pump storage scheme. And if it's below 5, you might have a good feeling about it, and especially developer will think it's kind of affordable plan. Between 5 and 10, it's unacceptable, and definitely above 15, it will require complex engineering and construction activities, and definitely it will be expensive. The example here goes to Snowy, where we have this ratio around 30. Another feature that I would like just to introduce, especially in comparison with generation plant, is the energy vs power. So in this case, as you can see on the graphics, an energy system, a generation system is practically defined by the installed energy, the installed power, sorry, But a pump storage scheme is practically defined by both, so the installed power and how much duration it can generate for energy transition. So this kind of feature, it's always good to think about. Now, typically, pump storage are easily designed for at least 10 hours of generation, which defines the energy. Another feature, which is kind of design choice, is what we call the hydraulic short circuits. Hydraulic short circuits are practically, let us say, a hydromechanical and a layout feature that allow to offer kind of flexibility to the plant. I would like always to propose this kind of feature when it's feasible and when it's easily done. So in practical, if we are not able to provide such flexibility by maybe reversible turbine or ternary system, we can practically pump and generate using the different units to allow maybe a good regulation of energy output from 40 to 100%. In pumping, practically the steps are 100% of the installed unit. This kind of feature of hydraulic short circuit is something that, as designer, we would like to propose. Another aspect that I would like to call the attention to is the hydraulic short circuit combined with generation of vortexes practically at what we call shadow vortexes at the downstream of the bifurcations. This is a CFD model made for Snowy, where we identified practically the formation of vortexes. As you can see, this colored cells going to unit number 6. And these vortexes practically, they might generate let's say additional vibration to the spiral case. They might reduce the duration of the hydromechanical equipment. So we need to understand these phenomena to practically decide also the length of the penstock required to dissipate such vortexes during hydraulic short circuits. Another design choice is variable speed via fixed speed. This is kind of a big question that being asked recently. It's not only because of design choice, but because of capex investment. So on the left hand side you have the fixed speed units, and on the right hand side you have the variable speed unit. Variable speed unit could be practically divided into two. The easy one and the less expensive one is a variation between -10 to 10% in rotational speed, while the fully flexible one, which require big civil infrastructure, if it's especially underground, this is the full converter variable speed. Those are really major scheme that needs to be understood from the capex perspective, but it will give a very, very good flexibility and services to the grid. This is a table that I shared with you about, let us say, the limitation of fixed speed and the pros and cons for variable speed. I will not go through detail, but I can say fixed speed, there are still pretty much the preferred choices for the developer because of their, let us say, confirmed or validated technology throughout the years. And sometimes it offers some services, especially for grid stability, using the inertia without having to use the variable speed with all the electronic equipment. I will not go through the detail, but it's a good table to share with you, and when you have time, you can look at. Definitely, variable speed unit, it will increase the cost of electromechanical equipment, but also the capex. However, if we go to the variable speed, as you can see here on the graphics, it will allow to have a wider head variation on the, as you can see on this vertical axis. the head variation that is present for the hydropower plant for the variable speed is way bigger than the allowable head variation in red for the fixed speed. But it also presents a wider range of power output adjustment. Typically, variable speed, as you can see here on the green line, is a very limited, fixed speed is a very limited discharge variation, while the variable speed is way bigger. Another hydraulic feature that I would like to share here is the design of the inlet-outlet works. As a hydraulic designer, we used to design an inlet structure, used to be intake structure, used to be called intake structure for one single direction of a flow. However, for pump storage, you have to think in both directions. And here, this is the example of Snowy. On the low red graphics, you can see the initial design of the intake, where practically during generation, the intake had all the velocity field concentrated in the middle, and we had practically to double the length of the intake to be able to answer the requirements of the intake structure in generation, where we have a way more uniform flow. So those are something that we should look at when we design a pump storage scheme, especially the intake and all the environmental requirements regarding velocities. So the role of pump storage in energy transition is very important. You can see here a typical graph. This comes from Italian experience. This graphic shows the power demand during a typical day. As you can see here in the middle, we have midday. We have the photovoltaic output, and it will be used practically to fill up the reservoir and consume the energy. It will become the load. So this is typical graphics. Also on the low right, you can see the sun variation and the wind variation. So practically, in addition to the seasonal and weekly and daily energy transfer, we are talking about using pump storage scheme also to answer intermittent loads coming from sustainable energies. And these loads sometimes might really generate issues. And one of the issues is the frequency stability of the grid. As you can see here on the graph, when everything is green, this is cool. But when on the right-hand side, things are getting really bad because the production is becoming higher than the load, so than the consumption. Then the frequency might change. In Europe, the frequency we are 50 hertz. In North America, it's 60. So the purpose is to maintain this frequency stable. And this is where also the ancillary services coming from pump storage scheme help us going back to the 50 hertz frequency when it's needed. So it can vary production or generation to maintain the frequency as required. This is a list of some ancillary services that pump storage will allow. So definitely it have a very reactive power support and voltage control. We can have also the black start, frequency regulation services. Spinning reserve is something that we use it a lot in Switzerland, and this is also available for the fixed speed turbine. Energy arbitrage is some ancillary services that also in Switzerland is very practiced. It's not very common in all the market. We see it in Australia or in Canada. Synchronous inertia is practically kind of physical property of a pump storage scheme where the rotor is rotating and helping automatically stabilizing the frequency of the grid. So this is a list of ancillary services that the pump storage will really be able to provide. in addition to the normal services, which is energy transfer. I wanted just to share how we regulate the energy, and this is one example where we have a blackout typically in France, and during practically kind of 30 seconds, we have the primary ancillary service will kick off, increasing slightly the frequency. Then after 5 minutes, we have the secondary power plants that are available to regulate better the frequency and reach by then the 50 Hertz required. And then comes the tertiary, which are like typically major power plant where are available at the request of the grid operator to kick off or to start to reach the final stability of the grid. This example related to grid regulation and blackout in case of use of ancillary services for pump storage. Another design challenge is
so much,
yes?
Salim. I just want to make you aware that we would like to move over to Q&A because I see that we have a very active chat and we'd like to go through some of it.
Yeah, sure. So should I continue, Bente?
Yes, if you can just wrap it up quickly, it would be great.
Yeah. Okay, maybe I would just share the design challenges related to fatigue. So definitely considering the cycles of pump storage, we need to understand the fatigue design for concrete lining and issue related to durability of the reinforcement. Since we will have cycling all the time between pumping and generation. Also, maybe the last slide is related to steel liner, which is part of the biggest capex we have in a pump storage scheme. So typically, we are seeing a very common way of designing steel liner based on fatigue, not only on external or internal pressure. So understanding the fatigue feature and the durability of major scheme of the pump storage scheme is very relevant at the beginning. Thank you all.
Thank you so much, Salim. And I think that what this presentation demonstrates to me is that we have an opportunity to tailor the design of pump storage hydropower plants to really provide these services to the power system that we are seeking. That said, that can also be quite challenging because we are aware that pump storage hydropower plant have an expected lifetime of more than 100 years. And if you are to have a crystal ball to look into the future for what kind of services the pump storage would be able to provide in 100 years, and what are the expectations of the power system, it is a very interesting thought exercise. But I wanted to ask you, Salim, if you were to focus the design on key elements for meeting future requirements for the power system, what would be the main ones?
So I think you said it extremely right, Bente. We've been faced about one of the unknown aspect of how the grid will evolve during the next 20, 50, 100 years. Snowy Hydro 2.0 is being designed to 100 years of operation without major maintenance. And practically, after discussing with the government, it was decided that we need to provide a very flexible power plant because we don't know how solar energy or the wind energy will come, how the grid will compensate the services that a pump storage will, grid operator will compensate the services of a pump storage will be offering. So typically on Snowy, we decided to apply 3 units of fixed speed and 3 units of variable speed. And this is a way of being prepared or how in the future will evolve regarding compensation of ancillary services and the requirement the physical requirement of the grid related to voltage and frequency regulation.
Thank you so much. And I think that this also brings me into the next question that is also captured by several of our asked by several of our audience. And we noticed that in this presentation we speak about pump power versus energy and pump storage planning. So it's interesting for many to observe that pump storage hydropower is often described in terms of megawatts rather than energy stored. And I think that from my perspective, when we are exploring is also to start describing pump storage hydropower and hydropower in both terms so that we connect megawatts with energy storage. But from a system planner's perspective, how would you think that planners would consider this relationship?
When I think it's a good question, especially thank you also for asking that and the colleagues connecting to this call. Myself also used to define a pump storage scheme in installed capacity, but I think it gives the wrong number or the wrong idea. And definitely it appeared to us that adding the duration or the energy output of a pump storage scheme is a key feature to define how much service will be offering, especially for energy stockage, but also how much maybe the capex will be important. I gave specifically for that reason the experience of Canada, this Ontario pump storage, where we are building a 30 million artificial reservoir just to answer 10 hours of duration. So if we need to increase by 1 or 2 hours, this capacity will be huge. So I think this is something that we should start as developers or owners to start thinking about that. I would like also to give a couple of examples on the government side. In Canada and in UK, the government produced a definition of what we call long duration energy storage. And this long duration energy storage are practically now defined. We are talking between 8 and above hours of generation, and practically pump storage schemes are now officially classified also by energy output, not only capacity. And this is also something that is being compared typically with maybe other type of energy stockage where maybe they are less capable of such a big stockage. Typically snowy, we are talking about 135 hours of energy stockage. So this is also compensate the fact that maybe it's a capex demanding project, but we have very, very long energy stockage, and this allows a certain flexibility in managing the local energy needs. Thank you.
Thank you. So I think that brings us to several questions were also raised by others when it comes to the capital cost for pump storage hydropower. So I think that I would also like to bring in Nuruddin in this discussion, and please also chime in, Salim, as you can contribute.
Sure.
But what are the main cost drivers in pump storage hydropower projects, and how do costs typically break down between civil and electromechanical equipment?
Nuruddin, would you like to start?
Please go ahead, Salim. So far, we have not yet went into the details for our project, as feasibility studies have just started.
Okay. Salim?
Okay, so maybe a couple of words, and this is also another important example. Why? Because in opposite to a normal generation power plant, pump storage scheme are energy consumption. So they need more money to operate. They need money to operate. They consume the energy. So sometimes they consume up to 30% of the output they produce. And this is what we call, let us say, this is what it's being an issue, because to develop a pump storage scheme and to put an upfront capex, knowing that it's not clear how this project will operate and how it will be compensated by the grid operator or local government, capex then become a big major criteria that needs to be looked at. The statistics, at least what we know for now, is that they are still based on the installed capacity. So we are talking as a cheap maybe power plant megawatt installed of around 1 to 1.5 million, and as an expensive one up to 3 to 4 million US dollar per megawatt installed. Lots of project depends practically on the underground works and all the civil that definitely represent 60 to 70% of the capex. The hydromechanical equipment maybe 20 to 25%, in addition to the balance of plant, maybe 5%. One of the capex also related to this full frequency converter for, let us say, a variable speed power plant, where we decide to install to have this full flexibility. These power plant definitely they might become quite expensive, because you will have big electronic or the electrical equipment if they are underground, so you have to build new cavern for them. So this can really explode the capex. So practically civil works is 30%. It's like a typical generation plant, I would say. If we have long tunnels, this becomes really expensive, and this goes to what I exposed initially, this factor between length and height. So when we have long waterways, then definitely we have to think about their impacts on the civil costs.
I think that what we're sharing there is also aligning with the approximate share of cost that we observe in the projects that we are preparing in the World Bank group as well. So I think that one of our challenges is, of course, that we work with de-risking these perspectives to start with, and as the capex is a big part of it is civil works, and the more underground works you have, the higher risk there are. So one of those, what I observed from your presentations is, of course, also that many of these pump storage solutions that you show to, they have extensive underground works, and I just wanted to take the opportunity to emphasize that it is important to perform substantial geological and geotechnical investigations to try and mitigate that risk as far as possible. And then I also would like to bring in Noradin, because I think he would like to contribute.
Yeah, thank you, Bint. Actually, I want to bring one important detail when it comes to this cost aspect is the impact on the crisis in 2022. The inflation in terms of electrical equipment and so on. In Morocco, before, we used to have costs like around 1.2 million per megawatt, based on the project developed, especially at the moment. But since then, no plant has been built, and there's also fear about the impact and the inflation on the. So I would like to ask Salim, or if he has a kind of quantitative analysis on how costs have changed since 2022.
Yeah, maybe I mean definitely costs depend on the country. In average, the recent pump storage scheme we are working on, it was never below 1.6, 1.7 million. So, in average, I would say, and the actual cost is maybe 2 million United States dollar per megawatt installed. However, one of the major factor is the timeline of construction of pump storage scheme. We are not doing like batteries in 1 or 2 years. Any pump storage scheme, also with reference to the risks that Bente highlighted of excavating underground and the unknown geology, pump storage scheme can be easily being built between maybe 6 to 15 years, and this unknown on inflation and the price of steel and price of civil works and equipment is another factor why capex definition, it might really hinder the FID of a pump storage scheme. And I saw it on really lots of parts of the world where it took years to get the FID in place and understand the general holistic picture of a capex and the operation and how we can get this return on investment. So
Thank you so much, Salim. I am sorry to say that we need to wrap up our very interesting Q&A session there, but I would also like to hand it over to Rebecca Ellis for a few outgoing remarks. And Rebecca joined IHA in June 21. She leads the research and policy team works on pump storage hydropower policy. And this aligns, and her experience and knowledge in this field also aligns very well with what we have planned for the next webinar. So over to you, Rebecca.
Thank you so much, Bente, and thank you so much to our fantastic speakers, from Fanny's wonderful introduction all the way through our technical findings on Noureddin and Salim's presentations. I always love to hear from our engineers and World Bank colleagues. I think it was great presentations. IHA is delighted to be supporting the World Bank ESMAP on this initiative. We are the Global Voice of Sustainable Hydropower. We're a nonprofit membership organization, and we represent the sustainable voice of the hydropower sector. As we've noted from Fanny, this is a more important issue now, more so than ever. As countries are moving away from coal and gas, the grid is becoming more dependent on these variable renewable energy, and so we have to consider this long duration energy storage. And pump storage, as our speakers noted, provide really important grid reliability and services such as system inertia and that synchronous inertia that Salim touched on. More so, we're seeing that governments are seeking to address this, and it's so wonderful to have ESMAP do this. As noted in today's presentations, we heard about how Morocco is planning and considering this in the next few years, and we look forward with anticipation how the World Bank will be supporting that initiative in Morocco and those fantastic projects. In addition, it was great to hear from Salim touching on the basics and providing those introductory technical remarks on how we can best support pump storage and understanding those technical things that all persons should be considering, from variable speed to head height to reservoir size to on river, off river. And IHA did support an initiative last year with the sector, the Enabling Investment in Pump Storage Guidance Note, which provides some high-level guides should any persons be interested in finding out more. It covers markets and revenue, development risks, and allocation risks, or how you do contractual. And on that, I would note If you enjoyed today, and I saw lots of questions actually in the chat about barriers and policy, we would strongly encourage you to save the date and join us on the 5th of March for the next World Bank ESMAP webinar on pump storage. This will cover policy and regulatory frameworks for pump storage hydropower. So please do join us again in about a month's time. And thank you again to those excellent speakers for providing such a great introduction to pump storage. And thank you again to Bente for her excellent moderating.
Thank you so much, Rebecca. And I just wanted to emphasize what you said there. Please do join us for the next webinar. We will go through and explore the topics of regulatory framework as well as policies. So hope to see you again. Have a wonderful day and afternoon.